Hello everyone, this is our session 2 on matrices. Okay, so in the previous session we had done some basics of matrices that we studied in class 11th and we did some row transformations, column transformations, some examples and the same. Okay, today we are going to study about inverse of a matrix. So let us begin with what is an inverse of a matrix, square matrix. Okay, so let us say that A is a square matrix of the order m into n, m into m. What does it mean m into n? That the number of rows are equal to the number of columns, and that is why A is a square matrix of the order m into n. Then we say that A inverse is equal to I, that is A m into n, that is m matrix, multiplied by A inverse is equal to I. This A inverse over here is called as inverse of matrix A. Okay. Now let us learn what are the properties of this inverse. Okay. First, A inverse is equal to I. That means when I multiply the matrix A with its inverse, the answer is an identity matrix. This is the first property. Second property, A inverse exists only if, okay, very important, only if determinant of A is not equal to 0. Okay, this is very important. That means any square matrix will have an inverse only if its determinant value is not equal to 0. So the very first thing when you start a sum on inverse is check whether it has a determinant value as 0 or not. If it has 0, then there is no inverse to that matrix. If it is not 0, then there is a inverse. Okay. Then here A inverse, okay, the third property has the same order, okay, as A. So important, what is the order of an inverse matrix? It has the same order as A, okay. Then every square matrix, okay, every square matrix has a unique inverse, okay, has a unique A inverse. That means the inverse of any square matrix is unique. There cannot be two different values of an inverse of a matrix. Okay. So important points to remember about inverses. First, let's go back and check the points. So first one, A inverse is I. That means when I multiply a matrix, a square matrix, okay, with its inverse, the answer is an identity matrix. Secondly, A inverse exists only if determinant value of A is not equal to 0. That means it is a non-singular square matrix. Only then will A inverse exist. Okay. Then the third one is A inverse has the same order as A. Okay, and last one, every square matrix has a unique A inverse. That means if the inverse exists, then it is unique. There are no two such values. There will be only one such value. Okay. Now, normally we write inverse as AB equal to BA equal to I. Okay. If this is the case, that if you're multiplying two matrices and you're getting the answer as I, then B over here, okay, B is the inverse of A. So if I have something like AB equal to I or BA equal to I, then B here is called as the inverse of A, and so we write it as B is equal to A inverse. Now if B is equal to A inverse, then the equation that we just wrote becomes A inverse is equal to A inverse A is equal to I. Okay, wherever there was B in this equation, I have put in A inverse. Okay, so if I have two matrices, square matrices with same order, and I multiply them and I get an answer as the identity matrix, then one is the inverse of the other. Okay, so here we can say that B is the inverse of A. Okay, now we need to know how to find this inverse. Okay, so for that, there are two methods. Okay, so two methods to find inverse. What are these two methods? So the first one is, it's called elementary transformations, elementary row and column transformations. Okay, and the second one is called as adjoint method. Okay, so today we will study about the elementary row and column transformations. Okay, so we have to study about elementary row and column transformations method to find the inverse. First of all, what is the procedure of finding the inverse? Now, if I say that A inverse is I, that means when I multiply the two, I get identity matrix. Okay, so I have to convert this A matrix that is given to me into an identity matrix. Okay, I A inverse is equal to B. Now, what does this mean? I'm going to use elementary row and column transformations on the matrix A, okay, and convert it into an identity matrix. But the rule of matrices says that if you are working on a prefactor means something that comes before what you are finding. Okay, so I'm finding A inverse and I am working on A. Okay, so if I'm working on the prefactor, whatever I do to the prefactor, I will do to the right hand side identity matrix. Okay, similarly, if I had something like A inverse A equal to I, okay, here A becomes the post factor of what I have to find. So what do I have to find? A inverse. A becomes the post factor over here. Okay, again, whatever I do to the post factor, whatever transformations I apply to it, I will apply the same transformations to I over here. Okay, and when I do that, it gets converted to a different matrix called as B. Okay, A inverse here remains the same in both the cases. Now, what is an identity matrix multiplied by any matrix? It is the matrix itself. Okay, here also an identity matrix multiplied by itself, multiplied by any matrix is the matrix itself. Okay, so again I'm repeating what is the procedure. So we normally denote inverse as A inverse is equal to I. That means when I multiply matrix and its inverse, the answer is an identity matrix. Okay, here I have to find out A inverse. So I keep A inverse as it is, I don't touch it, but the matrix A will be used for transformations. Okay, now in the first case, this is our first case, A is the prefactor. In the second case, A is the post factor. Okay, in the first case, whatever I do to the prefactor, that means whatever transformations I apply to it will be applicable to the right-hand side identity matrix, this one. Okay. And finally, when I'm able to convert the given matrix into an identity matrix, on the right-hand side, I have converted the identity matrix into a different matrix, B. Okay. And so I have found out A inverse. Okay. Now, how do we deal with post factor and prefactor? So whenever I have A inverse equal to I, okay, that means when A is a prefactor, okay, when A is a prefactor, we apply only row transformations. Okay. Again, I'm repeating, when I have A as the prefactor, that is, it is before A inverse, then I apply only row transformations on both sides. Both sides means on right hand side and on the left hand side. Okay. Whereas whenever I have A as the post factor, that is, it is coming after the inverse, then I apply column transformation. So here A is the post factor. Okay, and I will apply column transformations. Column transformations on both sides. Okay, so while applying transformations, what do we have to do? We have to remember which side is the matrix, on which side of the inverse is the matrix. Is it before, that is prefactor? If yes, prefactor, then apply row transformations. If it is post factor, then apply column transformations. Now normally they will mention in the sum, apply row transformations and find the inverse, apply column transformations and find the inverse. If they have not mentioned, then check the relation that they have given to you. If they have given A inverse equal to I, that means A has become the prefactor, and now we will apply row transformations on both sides. If A inverse A becomes I, then it is a post factor, and then we will apply column transformations. Okay. Now let us do the first one. That is, if we have A inverse equal to I, that means A is the prefactor. Okay. If it is a prefactor, we have to apply column transformations. So how will we apply these column transformations? What do you have to do for row transformations, not column, row transformations? What do you have to do? We have to convert A into an identity matrix, okay, by applying row transformations. So let us say that A is a 3 by 3 matrix, square matrix, and the elements are denoted in this format. Okay, so if we have this as a matrix, a square matrix of the order 3 into 3, then the elements are denoted as A11, A12, A13. So 1 is the row, 1 is the column, row into column. A21, A22, A23, A31, A32, and A33. These are the elements of the matrix A. Now, when I have to convert this into an identity matrix, what does it mean? That A11, A22, and A33, all these three should be equal to 1, right? And all the remaining elements should be 0. That will be an identity matrix. So, if I have to convert this into an identity matrix, what are the transformations that we have to apply? Okay, so row transformations. Okay, to get an identity matrix. I'm mentioning the transformations that you should apply, or the order in which you should do the transformations to get an identity matrix. Okay, so the first one is reduce A11, that is the first diagonal element, to 0. Okay, first we will do this transformation. Sorry, to 1, not 0. Reduce A11 to 1. Then after that, reduce A21 and A31 to 0. Now what is A21 and A31? Let us check. A21 and A31. Okay, so this goes first, then we reduce this to 0. Okay, this goes second, A21 and A31 to 0. Similarly, what will be the next one? Second one, reduce A22 to 1. Now we will work on this second diagonal. Okay, so this is your third step. Reduce A22 to 1. Okay, and then what will you reduce to 0 then? Reduce A12 and A32 to 0. Which are these elements? A12 and A32 to 0. This is your fourth step. Similarly, what will be your fifth step? Reduce A33 to 1. That is your third diagonal element. Okay. And what are we left with? A13 and A23. So after this we will write reduce A13 and A33, sorry, A23 to 0. A13 and A23. So after fourth step, this is your fifth step, right? And this one is your last step. Okay, sixth one. So let me repeat the steps. The first one, reduce A11 to 1. That is your first diagonal element to 1. Okay, then what do? Below those, what are the elements? You A21 and A31. What will you do to them? Reduce them to 0. So then reduce A21 and A31 to 0. Okay, next. What is our third step? Reduce A22, that is your second diagonal element, to 1. Okay, and then what will be your fourth step? Reduce A12 and A32, that is in that column, to 0. Okay, then the last one, fifth one, A33, that is your third diagonal element, to 1. And the elements above it, that is A13 and A23 to 0. Okay, these are the row transformations you will apply. When do we apply row transformations? When A acts as the prefactor. Okay, it comes before the inverse. Similar kind of column transformations you have to apply, not these. There will be different elements over here. Okay, when you do column transformation. Also important to be noted, when will I do column transformation? When A will appear after A inverse, that is when A will act as the post factor. Okay. Now this is the explanation to how inverse is supposed to be solved. Okay. Now we will try and do some examples on the same so that it becomes clear how transformations are to be applied. First of all, let us see some examples to prove whether or not an inverse exists. Okay, so let us take some. Check whether the matrix is invertible. Okay, so let us see. First one, 2 1 4 2. Okay, now let's say that this is equal to A. How to check whether the matrix is invertible? Find its determinant. So how do we find the determinant of a 2 by 2 matrix? Multiply the diagonal elements and subtract. So 2 2s are 4 minus 4, or I'll just put in the arrows so you know. 2 into 2, 4 minus 4 into 1, 4. So the answer is 0. Now determinant of A is equal to 0. That means A is a singular matrix, okay? And therefore, what do we say? Therefore, A inverse does not exist, okay? Are we clear with this? How to find out whether a matrix is invertible or no? Let us take one more example for making this clear. We'll take a 3 by 3 matrix this time. So we have 1 3 2, 3 1 2, and 1 2 3. Okay, let's check whether this matrix has an inverse. So what do? We find its determinant. Let us start finding its determinant. So let's go with the first row, first column, hide it. So we'll write 1 multiplied by 3 minus 4 minus 3. Okay, second column, hide the column and the row in which the element lies. 9 minus 2. Okay, plus 2 multiplied by 6 minus 1. So we have 3 minus 4, that is minus 1, minus 3 into 9 minus 2 is 7, 21 over here, plus 2 into 6 minus 1 is 5, so 10. Now, minus 1 minus 21 plus 10 is minus 11, and so answer is minus 12. Now here we can see that the determinant of C is not equal to 0, and therefore we can write that C inverse exists. Okay, that means its inverse exists. So you have to find out the determinant value first and check whether the inverse exists. Okay, now if the inverse exists, then what we do is the next step is to find that inverse. For finding it, then we use the row or the column transformation. So let us do a numerical on how to find an inverse by row transformation. So let me example 1. We'll do row transformation. We take a simple 2 by 2 matrix to just understand first how to find an inverse. So A is equal to 1, 2, 3, and 4. Okay, this is your 2 by 2 matrix. How to first, what is the first step to check whether the inverse exists? So let us find its determinant value. Determinant will be 4 minus 6, which is equal to minus 2. So determinant of A is not equal to 0. Therefore, A inverse exists. This is an important step whenever you are solving a inverse sum. Find its determinant value. It is required to check whether it is a invertible or not invertible matrix. Okay. Now, if I write A inverse is equal to I. Okay, it means that A has become the prefactor. It is appearing before A inverse, so it will become the prefactor. Whenever we have A as the prefactor, we will apply row transformation. So A inverse is equal to I. Okay, write the matrix over here. Put A inverse as is. Okay, this is what you have to find, and here the identity matrix. Okay. Now, what is the procedure to find the inverse? The matrix A will undergo row transformations and we will change it into an identity matrix. Rule number 2, whatever you do to the matrix A, you will do same kind of transformations on the right side to your identity matrix. Okay, so let us begin. We are using row transformations. I'll just write the sum here again, so it's on one page. Okay, so this is your right first row transformation R2. Remember, what was the procedure to convert into identity matrix? You work on the diagonal elements first. Now here the first diagonal element A11 is already 1. So the next step we will apply now. The number below it, we are going to reduce that to 0. So how can I do that? So I'll say that R2 changes to R2 minus 3R1. Okay. So I'm going to perform row transformation on the second row. Okay. So first row as it is, 1 and 2. And then 3 minus 3, that is 0. 4 minus 6, that is minus 2. Okay. A inverse as it is. Same transformations we have up to apply on our identity matrix. So first row remains as it is. Second row, 0 minus 3 is minus 3. 1 minus 0 is 1. Okay. Now, the next step is to convert the second diagonal element, that is this element, into 1. So how can we do that? I will do R2 changes to R2 divided by minus 2. Okay. So this will be 1, 2, first row as it is, 0, minus 2 upon minus 2, that is 1, A inverse as it is, equal to, okay, 1, 0 as it is. Second row has to change, so minus 3 divided by minus 2 will be 3 divided by 2, and 1 divided by minus 2 is minus 1 divided by 2, okay. Yeah. Now, let us go to the next step. We've done 3 elements. The fourth element is remaining, that is A12. What do we have to do to it? We have to convert it to 0. So what can we write over here? Remember, we have to only do row transformation. So we will write R1 changes to R1 minus 2R2. Okay. So we will have 1. Now R1 is changing. Okay. So 1 minus 0, 1. 2 minus 2, that is 0, 0 and 1. Okay. A inverse is equal to, now remember row 1 is changing, so 1 minus 2 into 3 by 2, that is 1 minus 3 minus 2, then we have 0, minus of minus becomes plus, 2 upon 2, that is 1. The second row remains the same, nothing changes in that, 3 divided by 2 and minus 1 divided by 2. Okay, so we have minus 2, 1, 3 upon 2 and minus 1 upon 2. And if you observe, this has changed into an identity matrix. A inverse is equal to minus 2, 1, 3 upon 2 and minus 1 upon 2. Okay, so what can we say? Since we have identity matrix multiplied by something, it becomes the matrix itself. A inverse is equal to the value that we have got. What is that? Minus 2, 1, 3 upon 2 and minus 1 upon 2. Okay, this is your A inverse. Now, how do I know that this is the correct answer? So normally they also ask you to verify your answer. So how will we verify the answer? You have to do A inverse equal to I. That means you have to prove that when I multiply A with its inverse, I'm getting an identity matrix. So let us do that. We have A as 1, 2, 3 and 4. Okay, and we have A inverse as minus 2, 1, 3 upon 2 and minus 1 upon 2. Sorry. Okay. So let us multiply this. What will we get? First row, first column will be minus 2 plus 3, that is 1. Okay. Then first row, second column, 1 minus 2. Sorry. I'll just write the multiplication so it's easier for you to check. Minus 2 minus, sorry, 1 second. Yep. 1 into minus 2 is minus 2 plus 2 into 3 upon 2. Okay, this is your first one. Then the second one will be 1 plus 2 into minus half. Okay, then minus 6 plus 4 into 3 upon 2 and 3 plus 4 into minus half. Okay, let us do these and get the answer. So minus 2 plus 3 is 1. 1 minus 1 is 0. Minus 6 plus 6, 0. And 3 plus into minus is minus. So 3 minus 2 is 1. So yes, we are getting an identity matrix over here. Okay. So AA inverse is correct, and the inverse that we have found for A is also correct. This is how you will perform row transformations on the matrix. Okay. In the next session, we will work first on a 3 by 3 matrix. So it will give you a clearer idea of how to do row transformations. Okay. Then we will go to the next method that is called as the adjoint method to find the inverse. Okay, if you have any doubts in this session, do let me know. I'll be happy to repeat it for you. Thank you very much.